Hello students, we will, as we discussed in the last module, that in this module we will continue with the computation of the autocorrelation, periodic autocorrelation function of the spreading sequence PT, and we won't stop only with the autocorrelation function calculation, periodic autocorrelation calculation. We really wish to see how the power spectrum density of this spreading sequence look like. Our focus mainly will be on the ML sequence, because we understand that that is the most this is the mother of all the sequence, and it is largely used also in the practice. Recall that in the last slide of the last module we have established this equation of the periodic autocorrelation. This is a classical expression where if x t is a periodic function with a period of capital T, then the autocorrelation function will be given by r x tau. Remember, we are also considering that x t is a stochastic process and with WSS assumption, whereas which is actually Whiteside stationary assumption. That is why the autocorrelation function is only the function of the delay tau. It is not t comma tau, and c is an arbitrary function. It can be 0 also, but basically this is integration over one period of x t, and hence it ends up with the fact the period of this periodic autocorrelation function will be also capital T. Now we will proceed to compute the periodic autocorrelation function of PT, where we will assume that PT is having an ideal, it is an ideal periodic spreading waveform and it has infinite extent, and we will consider a rectangular chip waveform for our consideration, for our analysis. Remember here one thing, if PT, if the spreading sequence has a period of capital N, then definitely PT will have a period of n into Tc, because Tc is the chip period, capital N is the length of the spreading sequence. So, total time that you are having for this period, the time that you are having for this spreading sequence, it is equal to capital N multiplied by Tc. We know this equation is well known to us because it is infinite duration sequence PT is. So, he will be given by the series of the bits pi or the chips, it is not bit, it is a chip, the pi multiplied with the waveform associated with it psi t minus ITC. We have seen this equation earlier when we were considering the direct sequence spread spectrum system. And if we consider c equal to 0 and we try to calculate the autocorrelation function using the classical expression that we have shown in the last slide, then we will be ending up with the equation 1.31. What we have done here, instead of your x t and x t plus tau, I have just written this pi and pal, and corresponding shi's are written for pi, the shi was ti minus tc, and for L it is replaced by t minus LTC, and it should be added with a, we have a delay of tau, and the summations are kept outside of the integration because they are not related with any dt, and integration is running over 0 to NTC because in the c value that we have considered here for the analysis is equal to 0. So, and definitely if it should be averaged over capital T, earlier we saw here my capital T is n into Tc. If I consider now that this tau is equal to j into Tc, that means there is a j is a integer value and the delay is some integer multiple of the chip duration Tc. And let us also consider that this psi t is a rectangular chip waveform, and for rectangular chip waveform we understand that value will be 1 if for the duration of 0 to capital T, and it will be 0 otherwise. So, once we put all this consideration here, then Rp instead of tau it will be JTC, we will be ending up with Pi into Pi plus j, because this whole expression will give you the value is equal to 1. We define this Rp JTC as equal to theta Pj. Now, situation is such that this delay, that delay for which you are computing this autocorrelation function, need not to be always the integer multiple of the chip duration. Situation may happen such that you are getting a delay which is equal to integer time of t c plus small increment epsa. Epsa is always less than t c. So, within a duration you are getting, so if this is the chip duration, and you have got some j number of the TC shift, then after that it may happen that you have got another shift of amount epsa, which is basically a part of the next chip duration. So, for this what will be the consideration, or what will be the computation of your RP or theta p equivalently is our point of interest. And again, if for this analysis also we will consider that psi is having a rectangular waveform. Here see, following the way we have constructed equation 1.31, instead of this tau or JTC, I have placed JTC plus epsa. So, what will happen for one component of W, you will get for ITC, or it is JTC is equal to ITC. For T minus ITC, that shift will be there, and another one you will get for the extra shift for this epsa, and it will be added with a situation that, see, you will get one portion, one will be the from the existing chip and another will be from the adjacent neighboring chip, where actually due to the shift of the extra shift of the epsa you are entering into. So, the autocorrelation function now is not only confined within this TC, it is having some extra contribution from the neighboring chip, and that extra contribution is also getting reflected in both the cases. So, situation is you are fast integrating over a duration of say epsa, and then the remaining part is TC minus epsa. So, one part is TC minus epsa, another part is epsa. So, your autocorrelation function will run with for both of this. So, that is why the additive term is coming. One is from the epsa, another is from TC minus epsa, and these are the two stuff that you are basically taking care of for the for using it actually inside the autocorrelation. One is the original one and another is the epsa delayed portion, another is part is the tau minus TC minus epsa delayed portion you are trying to find out with the autocorrelation. So, incoming signal is as if coming, and because of this JTC plus epsa delay, part of it is getting collapsed with the TC minus epsa and part of it is getting collapsed with the epsa. So, the same waveform you are actually now taking with a shift, two different shifted version of this pulse. If we are again taking the value of the WTC as a rectangular pulse as we have discussed earlier, you will see that the earlier RP JTC plus epsa will boil down to this point if we substitute the value of this theta p and theta p plus theta p j plus 1 from where, from the consideration of these two equations, the way we the logic which followed here, and if we follow the same logic we will be ending up with two values theta p and theta p j plus 1. Remember, actually for TC minus epsa duration normalized to TC, you are actually getting the autocorrelation value with theta p, and remaining for epsa normalized to TC, if that period you are basically giving autocorrelation value for j plus 1th chip. So, that is why these two contribution are logically also it is followed and you are getting that. Now, we will recall that for maximal sequence, this substitution we generated for the random binary sequence, what is the autocorrelation value? We saw that it gives us a triangular function, and so by calling that one we will see that for maximal sequence by substituting from this 1.29, which was actually which was actually already discussed in the last slide and the last module. We will come back here and we will be able to see that this triangular function is coming up, and this guy will end up with a minus 1 by n part if my del value or the tau value, the delay is NTC shifted by NTC by 2. The value of this triangular function also we have seen, and if I rearrange this might keeping minus 1 by n earlier and this n plus n by n, and if we see that there is it is not a one period, it is a multiple period going on for which we are computing the autocorrelation function, and this period is running from minus infinity to, and I can run from minus infinity to plus infinity, as your PT is also running from minus infinity to plus infinity. So, this triangular function now will be summed over this I value, and there will be a delay of I into n minus I into NTC by TC. Over one period, this autocorrelation function, periodic autocorrelation function of ML sequence will boil down to the lambda, to the triangular function of tau by TC, which is basically the autocorrelation function of a random binary sequence that we have already seen earlier. In the next slide, we will plot both of them. I mean the autocorrelation function, periodic autocorrelation function of an ML sequence, and the one period autocorrelation function of random binary sequence. Both are having a duration of TC. We wish to plot both of them, we wish to superimpose both the plots in the next slide, only because we wish to compare the performance of this autocorrelation function of both the sequence. Remember, random binary sequence will be ending up over the period of the TC. This is over the period of TC. The random binary sequence will be ending up with this value, and maximum value is definitely always equal to 1. And maximum length sequence, he will actually, when TC is beyond, you are going beyond the TC value. So, for that duration we saw that it will give a value of minus 1 by n. Where from it came? It came from the fact that here we have realized that even if actually I is equal to completely 0 and there is no existence beyond TC, if you are trying to find out, so you will not have any autocorrelation portion like this, but you will be ending up with a value of minus 1 by n always. So, hence this minus 1 by n is contributing in the figure like this. So, beyond TC you are ending up with this minus 1 by n, and other values are going like this. And now, as I told that we are interested to check the power spectral density of this triangular function, we will take the Fourier transform of this triangular function to check the power spectral density. Any triangular function, if you take the Fourier transform of it, it should be written like this, and we will see that it ends up with a T sin square function, where sin square is given by sin pi x by pi x, and j is equal to minus 1. So, Fourier transform of a triangular function ends up with a sinc function. Now, we have seen that the series of a periodic autocorrelation which I am seeing here, this is an infinite series, okay, and hence this infinite series that is coming in the periodic autocorrelation function, it is a period of tau also, and so it can be expressed as some exponential, complex exponential Fourier series. And as we understand that the complex Fourier transform of a complex exponential will be always a delta function. So, for this infinite complex Fourier transform of the complex exponential will be turned down to a delta function. So, infinite series autocorrelation, the part of this triangular function who is having an infinite duration, Fourier transform of that will lead us multiplied of a sinc function multiplied with a Dirac delta function. And applying this identity and on what, on that autocorrelation function, and taking we understand that the power spectral density and autocorrelation function, they are the Fourier transform of each other. We will take the Fourier transform of equation 1.36 now. We will take the Fourier transform of this now, and we will use the fact that Fourier transform of these infinite triangular function will be governed by this expression, and hence we will be ending up with the expression 1.39, where the sine square and del is the contribution from this continuous triangular function infinite with infinite duration of with infinite series of triangular function which is periodic over tau, and this guy n plus 1 by n square will be the n plus 1 by n square will be the contribution from the other side, and 1 by n square into del f, that is the part coming when my series is not coming for I equal to 0. This is the contribution, and for I not equal to 0 running from minus infinity to infinity, we will be ending up with this section. We can prove this one actually putting y equal to 0 also, how this part is coming up. Now, if I try to plot this power spectrum density PSD, the next figure will show us how does it look like. See, we are having a series of the Dirac delta function, but it follows the envelope of a sink as usual we have seen. The maximum value of that envelope will be governed by this n plus 1 by n square, whereas for I equal to 0th location, this is a point of I, for I equal to 0th location, we will be ending up with 1 by n square, a delta function whose amplitude should be 1 by n square. So, we are ending up with this expression, which are ending up with this figure. Now, coming from there, entering into a PN sequence, a pseudo noise sequence or a pseudo random sequence. It is also a periodic binary sequence, where actually there is nearly some even balance between the number of the zeros and number of ones that are there inside that sequence. And this autocorrelation of this PN sequence over one period usually resembles autocorrelation of a random binary sequence. And this PN sequence, which includes the maximum length sequence also, these are heavily used for the in practice for spreading the sequences, because these are autocorrelation properties are really very useful for the code synchronization in the receiver. We prefer the PN sequence a lot. And why actually a lot preference is there, because for other sequence you will see the lot of the if there is not only a sharp peak, there are several peaks associated with the main peak of the autocorrelation function, and which hinders the synchronization, giving false lock to those peaks. And that is why we will be preferring the PN sequence from now onwards in our discussion. And to derive the power spectral density now with a direct sequence spray signal, which is spread by a periodic spreading sequence. Now, we will enter there. We would like to see what is the spectrum of direct sequence spread spectrum signal, which is spread by a periodic spreading sequence. We would like to start from the fact that now this is not only the autocorrelation we have to look into, we have to look into the average autocorrelation of the xt of the random binary process, random binary sequence xt. And by definition of the average autocorrelation function of xt will be given like this, which is basically the autocorrelation function with that of a delay tau, which is integrated over minus t to plus t period and over total 2t period, and this is the averaging where t tends to infinity. And the limit exists and may be non-zero if and only if the xt, the random binary sequence with which you are starting, it has some finite power and some infinite duration. If you think that the xt is a stationary process, then definitely your average value will boil down to the autocorrelation value of a Whiteson stationary process, that is R x tau. The average power spectral density, which is defined by the Fourier transform of this average autocorrelation, we will be defining it. We know that this is our standard equation for the direct sequence spread spectrum signal st was given by a dt pt cos 2 pi f c t. We knew that dt is a modulated data modulation, and it is modeled as a random binary sequence, because all the data that we deal with in a practical communication system, they are random in nature, and they are random binary sequences considered for this analysis. PT, which is a periodic spreading sequence, Fc is the center frequency, and remember, if we are having a random binary sequence, so the autocorrelation of this section, the autocorrelation value of this data will be given by a triangular function that we have already understood. Theta is a random variable which is uniformly distributed over a duration of 0 to 2 pi, open interval of 0 to 2 pi, and it is statistically independent of dt. So, neglecting the constraint that we understood that there should be a direct transition, the transition of the chips and the transition of the data should coincide for in both the direction. If we are neglecting that constraint on it, then the autocorrelation of this direct sequence spread spectrum signal will be given by this. How we are writing it? So, it is a autocorrelation. So, the same st is getting correlated with st, and so you will get a square by 2. This pt will be given pt with a multiplied with a delayed version of it. Because of dt, you will get a triangular function associated with it, and then cos 2 pi f c t will be there, and phi are not related, they are independent identical distributed, and they are not having any dependence on the value of the dt. So, we can exclude that also. And where this pt is the periodic spreading waveform, what we are interested in. Let us see in the next slide how that autocorrelation, from this autocorrelation function of 1.41, we will be ending with the spread spectrum, the power spectral density. And now, if I substitute the equation of 1.40, this one, and we use this relation, then we will be ending up with the RS tau function, where we understand that this is the contribution came from the data part, and pt plus tau can be now written as a form of rp tau. Cos 2 pi f c t was there. This rp tau was the periodic autocorrelation function of pt that we have already derived earlier. For a maximal length spreading sequences, and using the convolution theorem and using all the other preliminary equations of 1.37 and 1.39. So, if I take the Fourier transform of this guy, we will be ending up with the average power spectral density of this ML sequence, whereas this SS1 or SS1, SS1 f minus fc or f plus fc, any one of them, or SS1 any f value can be its equivalent low pass equivalent density can be computed like this. For a random binary sequence, if we are taking care of, then if the sequence is not ML, if it is a random binary sequence, so this average value will be ending up with the SSF value, and then this SSF value is given by this expression Tc sin square f Tc. And so, this is the understanding of this power spectral density of a transmitted direct sequence spread spectrum signal. So, that will be the spectrum will be a combination of two different autocorrelation, two different power spectral densities, PSD of the data multiplied with the PSD of the periodic autocorrelation function of the spreading sequence, and hence you will get a combined effect of both of them on the spectrum of the direct sequence spread spectrum signal. So, it can it will not be only either it won't be actually, the autocorrelation function won't be only triangular, or it won't be only governed by this RP tau. It will be always a combination of both of them. See, actually why we are ending up here, why we are so interested about the power spectrum density computation of direct sequence spread spectrum signal is because once you are unknown about the fact of the spread signal spectrum, then designing the front end section, designing actually the front end different receiver, inside the receiver front end different components, and identifying the optimal bandwidth, especially for the wideband filters that you need to capture, won't be feasible. Automatically the way the dispersing operation will go on, and after dispersing operation, how will you design the optimal width of the filter to capture the bandwidth of the signal of your own interest, and the portion that you need to cut off, which is not of your interest, to design that filter, that we call the interference rejection filter also. And to design that interference rejection filter, you should have the knowledge of the spread power spectral density. So, spread power spectral density will help you to design the wideband front end filters, both in the transmitter before transmission and also in the receiver, to capture that intended bandwidth. And then while coming to the dispersing operation, after dispersing also, once the spectrum is shrinked, that intended signal spectrum is shrinked, then to design the interference rejection filter properly, we need to design, we need to know the power spectrum optimal width of the signal that is getting shrink, and what exactly was the total PSD of the spread signal, so that we can nicely reject the interference. Because once actually we are multiplying the incoming signal with our intended PN sequence and the spreading sequence, we understand that though our intended signal bandwidth will be shrinked, but the interference, the bandwidth of the jamming signal or interference signal will be spread over a bandwidth of the spreading sequence. And the power spectral density there will be also the same power spectral density, and the same computation of your under the autocorrelation or the whole spectrum consideration of that will be continuing with that section. And hence the filter design will be totally governed by this PSD of the intended maximal sequence. And also these two different kind of the calculations of with ML sequence and with random binary sequence will help you to understand that the spectrum is really heavily dependent on the spread spectrum power PSD is heavily dependent upon the choice of the sequence. Once we are changing the sequence from the maximal to random or random to maximal, see the spectrum consideration is totally getting varied. So, the design of the wideband filters also will be keeping on varying based on the choice of the sequence.